Okay, welcome to Lesson 3. So in Lesson 2, we talked about using t-methods to calculate a confidence interval when we don't know the standard deviation of the population. Now, we're going to go ahead and look at performing a hypothesis test using t-methods. So remember, confidence intervals, they ask an open-ended, what is the average? We want to estimate the average. Hypothesis tests tend to answer more of a yes or no question, like, is the average different from blank? Is the average higher than this? That kind of idea. So here, one sample t-test. So it's called one sample because it's the idea we're only looking at one mean from one population. Next week, we're going to look at comparing the means between two different populations, and that would be a two sample t-test. So when we don't know population standard deviations, we can perform a one sample t-test that is going to have hypotheses that look very familiar. So it's going to be, our null is going to be, hey, mu is equal to some value. This mu naught, that's a number. And it's a number that doesn't come from the sample. It's nothing, no information from the sample whatsoever. It's a number that's claimed or of interest, but it comes from outside of the study itself. And you can have the not equal to, you can have greater than, you can have less than. If it's greater than or less than, that's a one-sided. You're only interested in finding out if the mean is higher, or only interested in finding out if it's lower. Versus if you have a not equal, you're interested in finding either direction. It could be higher, it could be lower, we're not sure. Our t-test statistic is going to look really similar to that z-test statistic. So it's going to be x bar, so the sample mean that we observed in the actual sample, minus what's claimed over the standard deviation from the sample. So this is the key difference, is it's not sigma because we don't know sigma, over the square root of n, our sample size. Absolutely, if you know sigma, jump straight to using a z-test statistic. However, t-test statistics go with s. So we are still using our sleep example. So they were interested in finding out, okay, well, we have our university students and we want to see what their sleep habits are. But somewhere here, so we have the National Sleep Foundation, and they claim the optimal number of hours for an adult over 18 is 7 hours. So 420 minutes. So a student is interested in whether or not this is what's actually happening. So they go ahead, they randomly sample 61 students at the university. They ask them, how many minutes of sleep per night do you get on average? And they get an average in that sample of 455 minutes and a standard deviation of 88 minutes. And here is our big question that we're asking, our question of interest, if you will. Is there evidence that the students are getting enough sleep per night on average? So it's not word for word what we would want to see, but it's basically getting at, hey, is the average amount of sleep per night of all students at this university, is it greater than 420? So we're looking at greater than, at least, getting enough. If they're getting enough, they're getting at least, if not more. So we're looking at more. If you're ever not quite sure, feel welcome to clarify with us. Hey, the wording on this, is it implying higher than? Is it implying lower than? We're okay clarifying questions like that. Okay, so just getting started here, want to ask ourselves, this is my question of interest here, minus my population here, is the average number of minutes per sleep per night of all students at this university greater than 420 minutes? Units are important. So my parameter of interest is going to be an average. I'm collecting minutes of sleep. I can average these. So mu is going to be the notation, And then in words, it's going to be the population average minutes per sleep for all students at this university. So my hypotheses, remember the null is dull. We're going to start out saying mu is equal to the claimed value. So if 420 minutes, and remember 420 minutes didn't come from my sample, it came from this National Sleep Association. We're going to say, you know what, it's what's claimed. Nothing interesting is happening, it's 420 minutes. My alternative though, is going to get at what I'm actually interested in, is, hey, is that average higher than 420 minutes? I want to know if they're getting, you know, at least enough sleep, or technically more here. And then note, I did include the units. If we have units, you should include them. Well, we're kind of sticklers for units. So then my significance level, it's going to be 0.10. So remember, my confidence level, if it's 90% confidence, it tends to go with 0.10 significance. If I did 95% confidence for my interval, it'd be 0.05 significance most of the time. So checking my conditions. So did we take a random sample? Yeah, we have 61 students. They were taken by simple random sample, yes. We want to know, is our sample size big enough for the central limit theorem to kick in? Also yes, because our sample size was 61. That's at least 30. I don't even really need to sweat like, hey, you know, what does the sample look like? 61 is going to be big enough for central limit theorem to kick in. And then our third one, do we know the sample standard deviation? Like, do we have sample information? Yes. So we can use T. If you know sigma, go to Z. If you don't know sigma, we have to use T. So yes, we meet this as well. So filling this in real quick. So my claimed that we're interested in is 420 minutes. What we actually observed was 455 minutes. The sample standard deviation is 88 minutes. N, we don't really usually use units there. It's number of students. 61 students if you want. Units. So my degrees of freedom, n minus 1. So 61 minus 1. That's just going to be 60. So I now have everything I need to plug in to calculate my t-test statistic. So what I observed is higher than what's claimed. Right off the bat, I know that my t-test statistic is going to be positive because what we observed was higher than what's claimed. Basically 455 minus 420, that's going to be positive. That's all I'm saying. 88 divided by square root of 61. So let me see. This is not math in my head kind of math. I can do the top. It's 35. Rounding here. It says 35 because the bottom rounding. 11 point. I think it's 26725. I ended up getting a t-test statistic of 3.106. So then my p-value. I'm going to need a t-table for this. So here, looking at these rows, my degrees of freedom were 60. My t-test statistic with 60 degrees of freedom is 3.106. And it's positive. That's handy to know. So I'm going to pretend that this is at 3.106. And I want this blue area, right? Because my alternative was mu is greater than. So I want this higher than area. 420 minutes. So what this comes down to is, first I need to find the row I want. Degrees of freedom 60. Conveniently, I have 60 here. Note, if not all the rows, like if I had degrees of freedom 62, there's not a row for 62. We round down. So round down if you have to round. So if round, for your degrees of freedom row, round down. And part of what that comes down to is if I had degrees of 62, I do have a sample size of at least 60. I don't have a sample size of at least 80. You want to make sure that your sample size is at least as big as the row you use. You'll get really similar answers either way, though, typically. So what I want in this row is I want to find where 3.106 lives. So if I'm looking between these two numbers, no, 3.106 is not between those two numbers. It's not here. It's not here. Look in here. It's between these two numbers right here. Right? So 3.106 is between these two numbers. That means I go up and say, oh look, my one-sided p-value is between these two. Note that they always writes them backwards, so my one-sided p-value, so that shaded blue area right there, it's between 0.001, I could even put another 0 there, and 0.0025. So then you have to ask yourself, is this one-sided, is this two-sided? If it's one-sided, good, we're done. If it's a two-sided test, we have to take this and multiply everything by 2. So I'd end up getting a two-sided p-value between 0.002 and 0.005. However, this is a one-sided test, so we don't need to multiply by 2. I'm just mentioning that you need to multiply by 2 because sometimes you will need to. But remember, you only need a two-sided p-value when you have a not equal sign in your alternative hypothesis. So if I want to do this on a TI 83 or 84, you can go to stat. They conveniently have a function called t-test. And so then you pretty much, you can either input the data if you have all of the data in a list, or you can put in the stats. And so 420 is my claimed amount. 455 is what we observed in the sample. There's my standard deviation from the sample. There's my sample size. You do have to tell it the direction of the sign in your alternative hypothesis. And then you click calculate, and it'll give me, here's my t test statistic, and here's my p-value. So my p-value, remember we said it was between 0.0025 and 0.0010. The calculator's telling me my p-value is equal to 0.0014. So if I look, it is between those two numbers. I'm happy. It should match. Whatever you're doing, it should match what you got in your t-table. Although we're perfectly happy with either. You can give us p-value equal to a specific number, or you could tell us the p-values between those two numbers. We're totally happy either way. Okay, so 4-part conclusion. What this means is give me the 2-part conclusion for the confidence interval, and give me the 2-part conclusion for the hypothesis test. Give me both of them. That's a 4-part conclusion. So here, this is my 2-part for the hypothesis test. With a really small p-value, you can say it's less than a small number. That tells me it's small. With a p-value less than 0.0025, we're going to reject the null, right? Small p-values are strong evidence at a significance level of 0.10. Honestly, it wouldn't have even mattered what significance level we were using. Our p-value is pretty small. So then here's where we use that that table that we have earlier, there's convincing or very strong evidence here that the average amount of sleeps of all students at this university that they're getting per night is greater than 420 minutes or 7 hours. The students seem to be getting the optimum. So this last sentence, it's just kind of a little, it's gravy, it's extra. But yeah, it does appear that yes, the students are getting higher than that average recommended amount of sleep. Then we have the write-up for our confidence interval. So with 90% confidence, the average amount of sleep all students at the university are getting nightly is estimated to be between 436.17 minutes to 473.83 minutes with a point estimate, so what we saw in our sample, 455 minutes. So that'll be my 4-part conclusion. So it's kind of goofy. Combine the two-part conclusions, but that's essentially what that is. So you can take the 2 templates and put them together. It doesn't really matter which order you put the parts in, though know that if you start mixing them around a lot, it can get really confusing to read for, typical any non-statistician or even statisticians. It's really hard for anybody to read if you just jumble the sentences. Okay, so for this sleep example, we want to know what is the probability we made a type 1 error. So things to consider is we actually determine what the type 1 error is. So remember, type 1 error is probability type 1 error. It's equal to our significance level. But remember, type 1 error is when you reject a null when it's not actually, when the alternative is true. So type 1 is, the alternative is true, but and so FTR is fail to reject. We fail to reject the null. So even though the null isn't true, we didn't have enough evidence to reject it. Oops. Okay, so what is the probability we made a type 1 error in the sleep example? So type 1 error, as a reminder, this is when you reject a null hypothesis when the null is actually true. And we usually don't have any way of knowing whether or not it's actually true or not. So type 1 error, the probability of type 1 error, we actually determine this. It's equal to our significance level. So the answer to this question is just going to be, well, what was the significance level we used? So 0.10. Does that mean, so we did reject, does that mean we made a type 1 error? Not necessarily. We could have, because we rejected. In fact, by knowing we rejected, the only type of error we could have made is type 1. If we had failed to reject, the only type of error we could have made is type 2. However, we don't usually actually have the ability to know if we made an error or not. We don't usually have access to that population information in the long run. So robustness and T procedures. So especially important, we want to know that the tests we're using are reliable, that their results are reliable, otherwise why use them, right? So the idea is if a test is robust, the outcome of the test is still going to be valid, it's still going to be reliable, even if not all the assumptions are met. So you really do want a robust test, because if for some reason you're not meeting all of your conditions, you still want the test to be valuable, right? Not just honestly garbage. Because if violating the conditions means that it's not reliable at all, you can't use your results at all. So absolutely, T procedures tend to be pretty robust. In particular, if you have big enough sample sizes, they do pretty darn well. So we're pretty happy with that. So it's not going to do as well if you have really small sample sizes and you like what your sample is it's skewed, or you have extreme outliers. We don't like that as much. And that's a big part of like, hey, we need a big enough sample size for that central limit theorem to kick in. And if you're taking a small sample size and you know that things are goofy, it's not going to work out well. But know that if you're taking a bigger sample size, it's going to probably be fine. So using the T procedures assumptions. So absolutely super important that the data is from a random sample. The idea is we want to be able to say that this sample represents the population. And if we didn't use random sampling somehow, it's really, really hard to say that. Sample sizes less than 15. So if you're taking a really small sample, you really want the data to be roughly normal. So generally you're going to want it symmetric. You're going to want it to have a peak in the middle. You're not going to want to have outliers. So you're going to want to have really nice looking data in your sample for us to believe that the population is roughly normal and that the central limit theorem is going to kick in. If you have samples of higher than 15, usually you can use T procedures as long as there isn't extreme skewness. So like a little skewness, okay, sure. But if it's extreme, if you have a bunch of outliers, you're going to want a bigger sample size than like 16. Specifically, so large samples, honestly, if it's clearly skewed, if there are outliers, usually sample sizes of at least 30 will do pretty well. So even if it's kind of goofy, at least 30 is pretty well. Just kind of keep in the back of your mind, though, I like to kind of throw this out there. There will never be a time I look at my bank account and see 30 and go, yes, I can retire, right? We are sort of equating a little bit that a sample size of 30 is close enough to infinity. And maybe outside of this particular condition, 30 is not really close enough to infinity for a lot of folks. But it's close enough for the central limit theorem to kick in pretty reliably. So here we are. We have an example looking at yearly advertising budgets. So we randomly select 21 companies. And we have a student that wants to create a confidence interval. And they're looking at it, can we use T procedures? So things to consider, 21 is the sample size they used. And this is the sample. So remember, if you have 21, it needs to basically not be extreme. It needs not to be really skewed. It needs to not have big outliers. Is that what we're seeing? Oops. So looking here, the data were for an experiment. No, honestly, this doesn't even sound like an experiment. It sounds like a survey. Yes, because the sample size is large enough. I'd argue, well, a sample size of 21 may not be big enough. Not if our data are really skewed. So, no, because the data are skewed and have outliers, I would go with C here. And no, not because the sampling was repeated enough times. Repeated sampling is a weird thing. It's not like taking a large sample. It's taking, whatever sample multiple times. We're not going to mess with that in ST202. So if we have a histogram from a sample of 11 observations that has mild skew, should we use T procedures? So basically we want to know if a sample size of 11 is going to be big enough. But remember what we said? If our sample size is less than 15, what do we need to see? I'm going to argue no. A sample size of 11 is not big enough if you know it's skewed at all. If it was at least 15, mild skew wouldn't be a big deal. But 11's probably just not going to cut it. So that's it for lesson 3. I will see y'all for matched pairs designs.